So we'll resume with a short talk session. The first speaker will be Sue Parkinson from University of Chicago on depth separation.
Yes.
Please, silence.
Yeah, so today I'm going to be talking about my research on the role of depth in neural networks. And when we talk about depth separation, what we're talking about is the gaps in behavior that exist between neural networks at different depths. So we know that if we give ourselves a very, very wide width, then we can approximate pretty much any function we care about very, very well. But there are functions that you can approximate with many fewer ReLU units using a deeper neural network. And there are also functions that you can represent with much smaller parameters using a deeper neural network. But at the end of the day, what we really care about is generalization and learning. So, what if we just give ourselves very, very wide neural networks and we only care about approximating instead of exactly representing functions? Do we still get some sort of gap in not just the ability to approximate or represent functions, but in the ability to learn these functions in terms of sample complexity and generalization? So I'm sure this is very familiar with all you, so I'm just going to breeze through this. So we're going to assume that we've received data from some distribution with the deterministic labels y equals f of x. We're going to receive training samples, and we're going to use some learning rule to pick a model out of some model class based on our training sample. So for example, we might try to minimize the sample loss. We want, at the end of the day, to get good generalization error, which is just the expectation of our loss over the full distribution. But of course, we can't actually get this all the way down to 0 because we're only going to be using finitely many samples, and we're going to be using a limited model class. So we can only hope to be probably approximately correct. And by probably approximately correct, I mean that with high probability over the training samples that I receive, my generalization error will be less than epsilon. And if I have a learning rule that gives me a model that is probably approximately correct, using m samples, where m is allowed to depend on epsilon and also the probability, the failure probability delta, then we say that we can learn with sample complexity m. And we often end up with generalization error bounds that look something like this. So we're bounding our generalization error by the approximation error and the estimation error. The approximation error is the error we incur by using a limited model class, and we can bound it by just finding one good approximator in our model class. And then our estimation error, we typically bound this by bounding the size of our model class. And this is the error that we incur by only having access to finitely many samples. Okay, so this is a neural network. I'm sure you guys are all very familiar with this, of course, by the end of today. But yeah, just for some notation, this is the neural network I'm going to be looking at. So we've got a bunch of ReLU layers in our neural network. And then we're going to look at this learning rule, which is minimize the sample loss plus some L2 penalty on the parameters. So this cost CL of theta is the sum of squares of all the parameters in my neural network. Okay, so this is the learning rule that I'm going to be thinking about. And using this learning rule, if I change my architecture from depth 2 to depth 3, what changes in terms of my ability to learn? So let's just talk about some first-pass intuition here. So first of all, both of these model classes, if I'm giving myself very, very wide width, I can approximate pretty much anything I want. And if you just squint at this, you're like, oh, look, depth 2 has fewer parameters, so that should be a smaller model class. So you might think that, well, depth 2 is just going to have better generalization overall. But this first-pass intuition needs some revising. So first of all, we have the separation in width to approximate. So there are functions from RD to R that require width 2 to the d to approximate to within a fixed epsilon in depth 2. But you can approximate them with polynomial width with a depth 3 neural network. So the mathematical formulation of the question that we're really thinking about here is there a function from RD to R and a distribution on inputs x in RD that requires 2 to the d samples to learn to within a fixed epsilon and delta in depth 2 using this learning rule? But we only need polynomially many samples to learn with a depth 3 neural network. And the answer to this question is yes. There is a function that is hard to learn with depth 2, but is easy to learn with depth 3. And the way to pick this function f, or f sub d, is to pick a function that requires very, very large number of parameters to approximate it with a depth 2 neural network. But you can approximate it with a depth 3 neural network using small norm parameters. And just to give a little bit more detail, the function that we actually end up using is this f up here, which is a composition of a very oscillatory sawtooth function with a inner product. And this previous work on width to approximate showed that these kinds of functions require very, very large width and to approximate in depth too. And we showed that these functions also require large norm of parameters, even if you give yourself arbitrary wide width to approximate in depth too. But they're very natural to approximate with a depth 3 neural network. So you can approximate this inner product with one hidden layer, and then you can exactly represent the sawtooth with a second hidden layer. OK, so what about this opposite question? What if I want to, are there functions from RD to R and a distribution on inputs RD that I only need polynomially many samples to learn with depth 2, but I require 2 to the D samples to learn 2 to the D samples to learn in depth 3? And the answer is no. If FD is going to be easy to learn with depth 2, it is also going to be easy to learn with depth 3. And the key here is that if I can approximate with small norm parameters in depth 2, they can also approximate with small norm parameters in depth 3, essentially just by adding an identity layer. So a little bit more detail here. Maybe not because of time. But yeah, basically if I can learn with depth 2, then I can find a neural network that well approximates my target with the norm of the parameters being polynomial in dimensions. That's the C2 of theta epsilon is small. And because of that, C3 of epsilon, so the cost to approximate with the depth 3 neural network is also small. And if you choose your lambda for your depth 3 learning rule in a reasonable way, you can show that the output of your learning rule will also have small cost. So when we're looking at bounding our generalization error, we can restrict ourselves to only look at depth 3 neural networks that have small norm, instead of just looking at neural networks, say, with bounded width or something. We're giving ourselves arbitrary wide width, but bounded norm. And if we look at that, then we can use Rademacher complexity arguments to show that our generalization error will be small. OK, so at the end of the day, what we've shown is that functions that are easy to learn with depth 2 form a strict subset of functions that are easy to learn with depth 3. One caveat here is that so far I've only talked about functions that are exactly minimizing the objective. In our paper, we also generalize this to functions that are approximately minimizing the objective. But what about optimization dynamics and that whole mess? That's going to complicate things significantly. So it would also be interesting to think about how the loss landscape affects learning at different depths. OK, so I'd like to thank my fabulous collaborators and just advertise that I will be on the job market for a postdoc this year. So thank you very much.
You assumed the data was uniformly distributed. Can you extend this to other support assumptions, some concave distributions? Or?
Yeah. So basically, what you need for the proof is to interpolate your samples from your distribution with a small norm depth 2 neural network. So if you give me a distribution and you give me a way to do that, then yeah, the rest is pretty false.
Thank you.